Hello and welcome. In this video, we're going to talk about what happens when we take the limit of a composition of functions. What happens when those functions are continuous at the value that we're looking at, and what happens when they aren't continuous at those values. So let's go ahead and jump right in. So if we are considering the limit as x approaches a of g of x, and that's equal to the value k, and we have a second function that is continuous, this is really important, that is continuous at x equals k, then if we're looking at the composition, the limit of the composition, the limit as x approaches a of f of g of x, we can actually just take the limit of as x approaches a of g of x and take that value, which we said was k, and plug it into f. So we can really say that this is equal to f of k. Now the problem arises when that is not necessarily true. So if both of these functions are continuous at that value, you can just work from the inside out using the composition of functions. But if these conditions aren't met, meaning either f or g is not continuous at the a value that we are considering, or even if f wasn't continuous at the k value that we're considering here, that doesn't necessarily mean that the limit doesn't exist. It means that this property doesn't work. So just like in previous lessons when we talked about the limit as we approach something where there's a hole or where there's a vertical asymptote, and we talked about how sometimes there's other ways for you to look at what's going on. You can use conjugates, you can use factoring. You need to think about, is there a way to approach this problem in a different way than trying to use this composition property? So again, this doesn't mean necessarily that the limit doesn't exist. It means that we need to find a new way to analyze the limit that we're being asked about. So how do we do that? We need to go back and think about what it means to be a limit. We know that for a limit to exist, the left side must equal the right side, and that must be the number. That's how we figure out that the limit does exist. So oftentimes, if we have a situation where we have an issue with continuity, what we need to do is consider the one-sided limits and see if the one-sided limits are the same. So let's look at some examples and see when this problem arises and when we can just work through it in a more straightforward way. All right, so here we are considering the graph of f on the left and the graph of g on the right. And we're being asked to consider each of these limits and determine whether or not they exist. So the first one is the limit as x approaches 1 of f of g of x. So let's see what happens as we approach 1 in g. So if I look over here at g, as we approach x equals 1, it looks like we're at 0 as we approach 1, this point 1, 0. Now f, we have to ask ourselves, does f of 0 exist? Because that would be the k value we were talking about. If we have issues with that value, then we have to look at one-sided limits. But if we don't have issues with that value, we can just use direct substitution. So f of g of x, well, we said that g of 1 is equal to 0, and we don't have any issues with existence. Our function in f is continuous at x equals 0, and what that means is we can just work through this as this is the same thing as f of the limit as x approaches 1 of g of x, and we said that that inside limit is equal to 0, which means we can just look at our graph to see what f of 0 is. F of 0 is 2. So the limit as x approaches 0, the limit as x approaches 1 of f of g of x is equal to 2. Now let's go ahead and look at number 2. The limit as x approaches 2 of f of x and g of x. So now I'm talking about the product of these two functions at 2. So I need to ask myself, well, are they both continuous at 2? Because if they're both continuous at 2, properties of limits say I can find their limits separately and multiply them together. But if they're not both continuous at x equals 2, then I need to find a different way to evaluate this limit. So I'm looking right away over here at x equals 2 in f, and I have a jump discontinuity. It looks like everything is okay over here, but not in our f function. So we need to go to one-sided limits. So I need to look at the limit as x approaches 2 from the left of f of x times g of x. And this limit is going to be equal to, if we're coming from the left in f, coming from the left, that's going to be 0, which actually means it doesn't really matter what g is. Coming from the left is 0 times, this looks like it's, I don't know, approximately 1, but 0 times approximately 1 is going to be 0. So this equals 0. We're saying 0 times approximately 1. I just want you to see that. Now I need to see what's happening from the right. So the limit as x approaches 2 from the right of f of x times g of x. Coming from the right over here, this is going to be 1 times, this is approximately 1. And again, it's okay that we don't know the exact value. 1 times approximately 1. All we really care about is this limit going to be equal to this one? And the answer is no, these are not the same. So we can say, therefore, the limit as x approaches 2 of f of x times g of x does not exist. In order for it to exist, the limits from both the left side and the right side have to be equal, and in this case, they are not. All right, number 3 only involves the first function, f, so let's see what's going on with this problem. This is asking us for the limit as x approaches 0 of f of x. Well, f is continuous at 0, and we can see that at 0 we would get 2. But the problem is that f isn't continuous at x equals 2. We have a jump discontinuity, which means the two-sided limit doesn't exist. That means that we have to analyze this function in a different way. So I'm going to just make a note that we did say that the limit as x approaches 0, of f of x, so not f of x, right? Just analyzing the inside function, this limit is equal to 2. But because f is not continuous at x equals 2, we need to consider one-sided limits. And what I want you to notice is that when we look at this limit as x approaches 0, we're approaching 0 from below. Whether we're coming from the left, we're coming from below, or coming from the right, we're coming from below. Because we're coming from below, under the function, that means when we consider our new limit, we're going to be looking at the left-sided limit. If we were approaching from the right, we would be considering, if we were approaching from above, then we would be looking at the right side. And we'll see examples of this as well. So the way that we can consider this is that we can look at the limit as x approaches 0 of f of x is 2. We can then look at the limit as x approaches 2 from the left, again, because we're coming from below, of f of x. And if we come from the left, that's going to give us 0, which means that's what the limit as x approaches 0 of f of x is going to be. F of x equals 0. We don't have to consider both sides because this green portion here told us that we only care about what's happening on the left. So we can look at the left-sided limit here to come up with our overall limit existing and being 0. Now that's a little confusing, so let's make sure we look at a couple more examples to really solidify that in. Okay, so here are a few more examples. We have a new graph of f on the left and a new graph of g on the right, and we're being asked to find these limits if they exist. So what I encourage you to do is go ahead and pause the video and see if you can get through any of these 3 problems on your own, and then unpause the video and walk through them with me. All right, so number 4, the limit as x approaches 0 of f of x times g of x. We'll notice that both f and g are continuous at x equals 0, so that means I can just take the product of their limits. The limit as x approaches 0 of f of x is 1. The limit as x approaches 0 of g of x is 0, so this overall limit is 0. Since they're both continuous there, I don't have to consider above or below or left-sided or right-sided. I can just jump right into multiplying their 2 limits. For number 5, the limit as x approaches -1 of f of x plus g of x. Well, with both of these functions, we have discontinuities, jump discontinuities, for both of them, which means I know right away that I'm going to need to consider one-sided limits. And I'm actually going to do number 5 down here so I have a little bit more space. So the limit as x approaches -1. Let's start from the left, of f of x plus g of x. If we look at the limit as x approaches -1 from the left of f of x, that's going to be -1. If we look at the limit as x approaches as x approaches -1 from the left of g of x, that's going to be -2. So this is going to be -3. Now I want to consider what happens if we approach from the right. So same limit, x approaches -1, but now from the right. If I look at what's going on in f, that's going to be -2. If I look at what's going on in g, that's going to be -1. So this is -3. Notice that these are the same. Both the left and the right-sided limit are -3. That means that the two-sided limit does in fact exist. Even though the functions have a jump discontinuity here, we can say that the limit as x approaches -1 of f of x plus g of x, this limit is equal to -3 because both the left and the right-sided limit were the same. All right, I'm going to erase this and make room for us to do number 6, and then we're going to look at 2 more quick examples, and then we're going to wrap up this video. Okay, number 6, the limit as x approaches 1 of f of x plus g of x plus 1. So if I look at f of x isn't continuous at x equals 1, but the limit exists and is the same from both the left and the right. What's happening with g, not as we approach 1, because this is as x approaches 1, but in here we're going to be approaching 2. So what's happening with g at 2? We have a jump discontinuity here. So we need to consider one-sided limits. So let's look at the limit as we approach 1 from the left. Limit as x approaches 1 from the left of f of x plus g of x plus 1. Again, we're coming from the left. So that's going to give me 2 for f and 2 for g of x plus 1. So this is going to be 4. And then if we look at the limit as x approaches 1 from the right of f of x plus g of x plus 1. From the right-hand side, f is still at 2, right? We said it's going to be the same limit regardless. So f is still 2. G of 1 plus 1 from the right, g of 2 from the right is going to be 3. So this is going to be 5. So notice these are not the same. Because they're not the same, we can say the limit as x approaches 1 of f of x plus g of x plus 1 does not exist because both the left and the right-sided limit have to be the same. Okay, let me pull up a couple more examples and then we will wrap up. All right, for these last 2 examples, we're tying in content that we've been covering all unit, but now keeping in mind how to deal with these unique situations. So I encourage you to pause the video, work through 7 and 8 on your own, and then unpause the video and see how you did. All right, hopefully you have had time to work on these problems. I'm going to give myself some more space and come down here. The limit as x approaches -4 of f of x over g of x, both of those functions are continuous, so in theory, you could just plug -4 into f and -4 into g and then divide them. But I'm hoping that you see our issue is going to come into play, that we're going to end up with 0 in the denominator, so that's not going to work. If we didn't have any issues with our denominator, we could go about it in that way. So instead, what I'm going to do is actually just write the functions there. Let's erase this. And see if I can use factoring or conjugates or any of those other things to simplify. So if I factor f and rewrite this limit, these x plus 4s are going to divide out, so there's a hole in the graph, which means the limit does exist, and I can just use direct substitution now to get -11. If we look at b, again, we're going to have an issue with the denominator, and I can see that just because we're using the same 2 functions. So actually, I'm just looking at the limit as x approaches 7 of the reciprocal of what we just had. So x plus 4 over x minus 7 times x plus 4. So we still have a whole, but now that issue is in the denominator. I can't use direct substitution to plug 7 in because I'm going to have 0 in the denominator. And I'm not getting indeterminate form. I just have a vertical asymptote happening here. So this limit is not going to exist. And then last, on number 7, we're looking at the one-sided limit. And we're looking at g of x over h of x. So the limit as x approaches -4 from the right of g of x, so x plus 4, over h of x, which is -2 times the absolute value of x plus 4. So one thing I want to point out, and I'm going to give myself some more space here, is that absolute value is just 2 lines. So splitting this up, you can actually rewrite this without absolute value. If we're approaching -4, then we're on the part of the absolute value function that's going down before it starts going up. So the equation of this part, really this absolute value function, is -x minus 4 if we're less than 4, less than -4, less than or equal to, or it's x plus 4 if x is greater than -4. So we can rewrite this as the limit as x approaches -4 from the right of x plus 4 over -2 times -x minus 4, since we're on the downward part of the line. What I want you to notice is that that negative sign can be factored out and that I can pull 1/2 in front of this limit, the limit as x approaches -4 from the right of x plus 4 over x plus 4. Well, this is 1, and 1 times 1/2 is going to give me 1/2. So that overall limit is going to equal 1/2. All right, let's look at number 8. I think I have enough space. I think this one's pretty straightforward. The graph of f of x is shown below. It has a vertical asymptote at x equals 6. Use the graph to find the limits if they exist, or if not, right, do not exist. So the limit as x approaches 2. As x approaches 2, there's a hole in the graph, but that doesn't make any difference for the limit. The limit from the left is the same as the limit from the right, and both of those are approaching the same value, which is -2. So the limit as x approaches 2 of f of x is -2. The limit as x approaches -1, and this is a two-sided limit. The limit as x approaches -1 is not going to exist because we have a jump discontinuity there. So we can just write does not exist. Part C, the limit as x approaches -1 from the left, we can identify that's going to be -2. And the limit as x approaches 6 is going to not exist since we have a vertical asymptote there. We could say that and in this case, we can't even say that the limit is infinity or negative infinity because we're approaching different infinities on each side of that vertical asymptote. So the key ideas in this section, which tied a lot of previous sections together, is that if we have a composition of limits, as long as we don't have any continuous issues or any issues with continuity, we can still use the direct substitution and work our way out from the composition of functions. If we do have issues with continuity, we need to consider one-sided limits. And if in that process we're coming from a function below, that means we need to look at left-sided limits. And if we're coming from a function above, we need to consider right-sided limits. So don't just always jump to a limit not existing because something weird is happening. Make sure that you're taking that extra time to analyze what's happening in a more complicated way. So go ahead and write down any questions you have, post them below the video, and I look forward to supporting you. Thanks for listening.